This is Unit 3, Topic 2, the standard normal distribution. In this section, along with the PowerPoint, you will also need the standard normal distribution tables. They are located both under the folder for this topic as well as the statistical tables folder under the main section in Moodle. So the standard normal distribution is going to bear a lot of similarities to the uniform distribution. Specifically, however, it is a special instance of the normal distribution where the mean is 0 and the standard deviation is 1 every time. So every time the mean is always going to be 0 and the standard deviation will be 1. In reality, there's not any real-world applications, or at least there's not many real-world applications that will fit the standard normal distribution. However, it is still going to be very useful to us because no matter what our scenario is, no matter what its mean and standard deviation, we can always bring it back to the standard normal distribution using something that we've already done before in Unit 1. So to emphasize the similarities that we'll see to the uniform distribution, first of all continuous probability distributions will have a lot of these things in common. But what we'll find that we can connect to the uniform distribution is that the area under the curve is 1, so meaning it represents 100% of the total outcomes. Areas and probabilities are equivalent, and the bottom axis is a number line. So besides the fact that they're continuous, that's kind of implied when they're both continuous distributions. However, with the normal distribution, the shapes that we're finding are not going to have a straight line on top, so they're not going to be perfect rectangles like we saw in the uniform distribution. If you remember the bell curve shape, which is the normal distribution, it's got a nice curve along the top, which means that the geometric area of that isn't going to be something that we can find at least accurately by ourselves. So some new considerations that we do have to make for the standard normal distribution. So first of all, unlike the uniform distribution, the bottom axis is going to go on forever in both directions. This is only in theory. Obviously, we can't have a negative weight of a person or, infinitely, many people in a statistics classroom. But we'll talk about in a little bit why this actually doesn't even matter, the fact that the theory keeps on going even after the practical sense stops. The other thing is the consideration that we just mentioned, and that the probabilities are not always easy to find because we're going to have a curve on the top instead of a rectangle. So one thing I am going to mention is that if you have taken calculus, the normal distribution, standard normal specifically, has this equation. So if you can put this into your y equals, a window of -3 to 3 and 0 to 1 on the y would give you a nice bell curve. So this equation can be used with integration in order to find the areas that we're looking for. However, if you've not taken calculus, not to worry at all. We don't need it in any sense, but it is interesting if you have taken calculus to see the connection there. We are going to be using probability tables, so just like the binomial distribution tables, as well as in a little while, a few sections ahead, we will have stata. So the picture is going to be the same as what we would have been used to in Unit 1, except for the mean is always going to be 0 and the standard deviation is 1. So we'll always have this bell curve shape here. The area of this is going to be 100%. It does go on forever in both directions. The curve gets so tight to the x-axis, however, that not really much is happening there. So the mean of 0 is in the middle, and each step up is worth a standard deviation, which in this case is always going to be 1. So this is the picture that we'll draw every single time we look at a standard normal distribution. So we have two reminders that we're going to do before we get into the calculations. The first is the empirical rule. The empirical rule said that for data that was approximately normally distributed, the following percentages would be true for the amount of data that falls within them. So within 1 standard deviation above and below the mean should be about 60% of the data. So that's a little bit more than half of this overall curve. So that should kind of feel like it makes sense. Within 2 standard deviations, there's 95% of the overall data. And within 3 standard deviations, we'll have 99.7% of the overall data. Coming up very soon, we will be able to find these exactly, or at least to 4 decimal places with the statistical tables and probably 6 with Stata. So we'll get to see how close these actually are, and they're not bad at all. So they were a pretty good set of values to use for estimates. Next is z-scores. I mentioned in Unit 1 that z-scores are really important, even if at the time they don't necessarily shine. But z-scores are going to be kind of something that we will use throughout the rest of the semester, or a very close equivalent. So in Unit 1, a z-score is a measure that tells how many standard deviations a value is away from the mean. So we'll be discussing those in more detail. We will still be calculating z-scores, but this unit we just need to make sure we understand that a z-score is a location of how many standard deviations a value is away from the mean. So here are the written instructions for finding probabilities using the standard normal table as well as in Stata. We're not going to be using Stata in this section, but I wanted to keep everything all together. The rest of the video will demonstrate using the statistical tables. So you don't need to refer to this unless you would like to. So there's 2 different directions we're going to be looking at here. The first one is I call forward because it is kind of the one we'll go more often. And that's finding an area given a z-score. Next, we'll be going backwards and finding a z-score given an area. So again, this is instructions for the statistical tables as well as for Stata. And we will be going through the tables in the rest of this video. And eventually we'll be coming back and getting Stata involved here. So let's actually try an example. You will need the statistical tables with you. So a certain process is normally distributed, has a mean of 0 and a standard deviation of 1. So this is the standard normal distribution. Answer each of the following questions by drawing a picture and using the z-score tables. So find the probability that a randomly selected item from whatever this distribution is has a z-score less than 1.45. So the first thing that you want to do is get a normal distribution with a mean of 0 and a standard deviation of 1. So I usually label this up pretty well. I'll label this from -3 to 3, even if I do this by hand every time. And so now what we want to do is we want to first draw in the z-score of 1.45 and then shade where less than is. So 1.45 is 1 and about a half. I usually don't nitpick. My usual question is it greater than a half or less than a half when it comes to the areas? One good thing about this section is that things kind of are drawn to scale in a way, or at least pretty close. So you'll be able to ask yourself if your answers are at least in the ballpark. So 1.45 falls in between 1 and 2, and it looks like I gave up and just put it right up where half would be. And less than is going to be to the left. So this is definitely more than half of this normal distribution. So when we do eventually find the area of the shaded region, I do expect it to be more than half. This is a good way to cross-check yourself. There's a lot of instances where you'll accidentally find the non-shaded piece. This will actually be pretty easy to do, so I definitely make sure you would always check yourself at the end. So does this make sense is one thing that you can ask yourself. So in order to figure out how big this area is, we are going to need the statistical tables. So this is a little snippet from the standard normal tables. And so what you do is you look up your z-score of interest. So I'm going to look up 1.4. So the leftmost column has the ones and the tenths place. and the 5 is going to be the hundredths place, and that's along the top row. So the area to the left, which is what all of these areas represent in this table, is 0.9265. This makes sense. It definitely seems like it's I mean, closer to 100% than it is to half. So that's usually what I try to do is it closer to 0, 50%, or 100? So find the probability that a randomly selected item has a z-score greater than 0.91. So here would be a picture of this scenario. We have our standard normal distribution. 0.91 would be somewhere a little bit less than 1. So what the table will tell you when you look up 0.91 is it's going to give you this area here. It always gives you the area to the left. So when you look up 0.91, you get 0.8186, which is this area, because remember, more than half, less than half is going to be your question. So what you're going to need to do is say, okay, this whole thing is 100%. So we're going to need to do 1 minus 0.8186 in order to get the 0.1814. So when you look up 0, so here, the way that the table is broken down is that there's negative. So here are the negative z-scores. And note the picture on the top is telling you it's the area to the left. And we want a positive 0.91. So 0.9, and then 1 is going to get me 0.8186. So this is going to be the non-shaded area. So in order to get the shaded region, we need to do 1 minus that. And that's going to be how it will work every time. So if you get something that you don't want and you want the whole other part of the distribution, you're going to do 1 minus that value. The other type of this example is finding the area between two z-scores. So this question says, find the probability that a randomly selected item has a z-score between negative 1.11 and 1.58. So here's the image for this scenario. This one is a little bit more complicated. So on the next slide, it's going to have a few different images. So in order to find the area in the middle, we need to look at two different cases here. So when we look up this upper z-score of 1.58, we get the part that we want as well as this other region that we do not want the area of. So what we have to do is we have to look up this z-score and find the entire area to the left, and then find the area of which we don't want, which is the area to the left of the lower z-score. Once we do this and we subtract the two values, we end up getting just the piece that we want. So originally we get the black plus this non-shaded left tail over here. We subtract off that piece that we don't want, and then we are left with the middle. So when you look up the upper z-score, you'll get 0.9429, and you're going to subtract from that this piece that we don't want, which is 0.1335. In the end, you'll end up getting 0.8094. This one is a little funky. I definitely recommend practicing the next 3 questions in order to make sure if you have this concept or not. So D says, find the probability that a randomly selected item is less than 0.27. Find the probability that a randomly selected item is greater than negative 2.25. And find the probability that a randomly selected item is between 0.53 and 1.31. So I would pause the presentation and draw pictures for all 3 of these, as well as using the tables to find the area of those shaded regions that you have made. So here are the solutions for those 3 questions. For D, the probability that the item is less than negative 0.27. So negative 2.27 will be a little bit less than 0. This is going to be less than half, but still closer to half than it would be to 0. So when you look up negative 0.27 in the tables, you'd get 0.3936. For E, negative 2.25 is again down below 0. When you look up negative 2.25, you end up getting this number right here, which is definitely not the area of the shaded region, because this is only about 1%, whereas our shaded region is much more than 50% and is closer to 100%. So you'd want to do 1 minus 0.0122 and end up getting 0.9878. So lastly, the area between 0.53 and 1.31 and between those z-scores, we would look up the z-score for the top that has an area to the left of 0.9049. So this gives us the shaded area plus this other piece. We can find out how large this is by looking up the lower z-score of 0.53 and subtracting it off, which is what we did here. So 0.7019, the subtraction of those two is 0.2030. So example 2 is basically going to be the same thing but backwards. I call this one the wild goose chase because it does involve looking through the tables, which is usually, I don't know, quite a process. It's not difficult, but it definitely is something that you'll get used to over time. So this is that same scenario, and for each of these questions, we're going to find the z-score given the area for the given area using the z-score tables. So the first one gives us a shaded area and tells us the size is 0.2119. So what you do is in the statistical tables, you want to find, so this is definitely a negative z-score. So you're going to go to the side that has the negative z-scores here. So inside the table here, I'm going to look until I find 0.2119, which is right here. And from this, we are going to construct the z-score. Now, one thing that will surprisingly help you, because sometimes it's easy to get these z-scores and probabilities mixed up, it's best to make sure that you keep consistent with your rounding. So if probabilities are always to 4 decimal places and z-scores are always to 2 decimal places, that will help some of the cases where you can get those mixed up. So if we were to construct this z-score, I would head to the left to get the ones in the tenths place. So this is negative 0.8, and then I'd go up to the top, and the hundredths place is a 0. So a z-score of negative 0.80 will have an area of 0.2119 to its left. So B gives us an area to the right. There's 2 different ways to deal with this. The PowerPoint is only going to go through one of the methods, but I am going to give you an alternative that is completely up to you and it will always work. So 0.8059 is an area to the right. However, the normal tables are the area to the left. So what you can do is look up 1 minus 0.8059, which would be 0.1941. That is how large this non-shaded piece is. Then from there, you go to the table and you start to look up 0.1941. Now what's going to happen in this case is 0.1941 is in between 2 values. It doesn't exist in the table exactly. So we could find this if we use technology. However, when we're using the statistical tables, we don't take an average or do anything like that. What we actually do is just choose the value that is closest. So in this case, 0.1949 is closer to 0.1941. So this is going to involve you being semi-okay with comparing decimal values. One thing that you can do is you can just take the decimal and move it 4 to the right for all of these numbers. So this is 1922, this is 1941, and this is 1949. So, I mean, working with these small decimal values is going to be a little bit more difficult for everybody because we don't typically have to use values that are that small all the time. So we're just not used to them. Whatever you do, you'll find something that will work for you specifically. Everybody is different when it comes to their method of deciding which decimal value is closer. Some people will subtract using the calculator. Some people will just see it right away, and other people will do the method that I just did with moving the decimal place out in equal amount. So this is the number we're going to choose. If we head all the way over to the left and then all the way up, we get a z-score of negative 0.86. So I would pause the slide and practice these last two on your own. We will get a chance in the next section to practice using the statistical tables a little bit more, but I would be comfortable with the examples that we have covered in this in order to be confident with the next topic. So the two pictures differ in which direction the area goes that is given. So for C, the area is to the left. For D, the area is to the right. So I'm going to go over an alternate way that you can do D. Either way is going to be up to you. So this is going to have a z-score of 0.33. This makes sense. It is a little bit above 0. It's positive, and it's closer to 0 than it is to 1. So you should always be able to ask yourself, does this value make sense, both for areas and for z-scores? Things aren't going to be drawn to scale 100% perfectly, but they will be close enough that you'll be able to tell if your answer is accurate in general. So secondly, over here is 1.54. I'm going to show you what can go wrong with this question and how it's not that bad if you're a little resilient. So what usually happens with this question is people are just, kind of saying, oh, okay, my area is 0.0613. So they head over to the tables and they look up 0.0613. So this is again another instance where we get close but not exact. Well, when you look up this value, you end up getting negative 1.54. The answer is a positive 1.54. So one option that you have is just changing the sign of the z-score. This will work every time, and it is because the normal distribution is symmetrical. So what you've basically found is this area down here. And so we can just mirror that above over 0 to this right area. Either way is okay. Honestly, it depends on how much I'm paying attention. Sometimes I'll end up saying, oh, hey, I have to do 1 minus. And other times I'll accidentally look up this value and then say, oh, I have to just change the sign. If you don't change the sign of the z-score, it is probably going to be completely wrong because negative 1.54 is pretty far away from a positive 1.54. So it's really easy to put it on autopilot, but when that happens, it's also going to increase your small mistakes. So always ask yourself, does your answer make sense? So lastly, my answers appeared, so I'm just going to leave them. The notation that we're going to get that is new for us is z sub alpha. Okay, alpha is going to end up being a pretty popular letter for us. Alpha is a Greek letter. It's a lowercase Greek letter. And so this is the only time where we're not interested in the area to the left right now. Eventually it's gonna be left or right depending on what we're looking at. So this is the z-score that has this much area to its right. So this first example, z sub alpha 0.05, has 5% of the area to the right of its z-score. So you can either look up 0.05 or you can look up 0.95, and either way you'll end up getting to 1.64 eventually. There is a consideration we have to make for this one. 0.05 is exactly midway between two numbers in the table. So I would definitely check this one out and make sure that you're getting the same thing that I am. But 0.0595 and 0.0505 are exactly the same distance from 0.05. What we're going to use in this case, I would not mark this incorrect. However, 1.64 is a very popular z-score. If we figured this out to more decimal places, this would round to 1.64. So every time that I have this choice, you'll find that I always use 1.64, and it's just because it's a well-known area in z-score. So I'm going to leave the last two up to you. As always, please feel free to email me if you have any questions. And again, as a reminder, please get this material down before you move to topic 3, because topic 3 is going to involve this skill exactly, but it's going to add a level to it.